Let's now start talking about even and odd signals. And there's not really too much to say because it actually works out quite simply in terms of the definition and sort of the intuition. So the first thing we'll do is we'll define what we mean by an even and odd signal. Let's start out with continuous time. So a continuous time signal, x of t, is said to be even if it satisfies the property that when you time reverse it, it looks the same. So if x of t looks the same as x of minus t. And we say that it's odd if when you flip it, it gets negated. So you can write this sort of either way you want. You know, if you want to think about writing it in terms of what happens when you flip the signal, you could say that x of minus t is x of t. I just happen to write it in terms of x of t being equal to something. And this one, what you would write is that x of minus t is equal to negative x of t. And so there are, some very simple examples of signals that satisfy these properties and that don't. So for some simple examples, we can look at x of t equals t squared. So this is just going to be a parabola. Which has the property that when you flip it around 0, it looks the same. So this is an example of an even signal. And then an odd signal, we can take x of t equals just t, for example. So now that'll be a line of slope 1 through the origin. And it's clear that if I flip this thing around the vertical axis, it's the negative of itself. And then, of course, there are signals that are neither even nor odd, lots of them. And one example might be an exponential. X of t equals e to the t. And so that signal, I'll just kind of sketch it briefly here. You know, it's going to go something like, so it's clear that if I flip that around the t equals 0, it's not going to look like itself, and it's not going to look like it's negative. So that's an example of signal that's neither even nor odd. And we can do the same thing for discrete time. The definitions look identical. So a discrete time signal, x of n, is even if everything kind of makes sense when I just substitute n for t. X of minus n is equal to x of n, and it's odd if x of minus n is negative x of n. Now, there's one signal that's kind of peculiar, and that's the all zero signal. So kind of a special case here. if we have x of t equals 0 and x of n equals 0, so the all 0 signals, these are both, if you look at the definition, both even and odd. But it's the only such signal. So this is the only such signal. Every other signal is either even, odd, or neither. Okay. I mean, that's kind of a fancy way of just describing this property of signals. And that says that I'm going to express it in terms of continuous time, but there's going to be an analogous result for discrete time. Every continuous time signal, x of t, can be expressed, and in fact, this is a unique decomposition theorem in the sense that it can be expressed in only one way as the sum of an even signal and an odd signal. So in other words, you give me my signal x of t, I want to write it as y of t plus z of t, where y of t is even and z of t is odd. And the claim is that you can only do that one way. So in other words, you can't give me two different ways of representing the signal as an even and odd signal. And in fact, the way you do it is by defining y of t to be equal to, well, it's got to be an even signal. So we take x of t, we add x of minus t, and divide by 2. Now you can check that if I plug in minus t for t, I get the same thing. So it's an even signal. And this is actually called the even part of x of t. And it's usually written as, EV of x of t. So it's the even part of the signal. And then z of t, you might be able to guess, we define it by taking x of t and subtracting x of minus t and dividing by 2. Now you can do a quick check here. If I plug in minus t for t, because of that negative sign, I'm going to get the negative of the signal. So it's odd, and we call that the odd part of x of t. And that turns out to be the only way you can do that you can represent it as a sum of an even and an odd signal. So to get an idea of what that looks like, let's take a look. Well, clearly if the signal is even, you can check from the definition of evenness, the even part of x of t, if x of t is even, is x of t. And if it's even, meaning x of t equals x of minus t, the odd part is going to be 0. So its decomposition is just, itself. Similarly, if it's odd. So it's only interesting when the signal is neither even nor odd. And then you kind of break it up into these two pieces, one of which is even and one of which is odd. So let me show you a picture of what that decomposition looks like for the signal x equals e to the t. So if I can find it. So let me, okay, so here is that decomposition. Everybody can see that. So we take the even part. It's e to the t plus e to the minus t over 2. That's actually the good old hyperbolic cosine function, cosh of t. The odd part is e to the t minus e to the minus t divided by 2. That's actually the hyperbolic sine function, the sinh function. So if you plot them, you can tell this is going to be the cosh function. You can see that it's even. It looks sort of parabolic. And then the sinh function is an odd function. And if you add, it's written here in terms of an axis x, but I think just translate that to t. If you add those two together, then the thing that you get, you can kind of try to visualize it. It takes a little bit, but you'll see that you actually get something that goes right through 1 and goes off to infinity. You get e to the t, or e to the x in that picture. Okay, so that's an example of an even-odd decomposition of a signal that is neither even nor odd.